Right. Holy Week. So last time we talked about the structures of protein, the hierarchy of protein. We started from the primary structure. No, for a primary structure, we always start from the N terminus end to the carboxy terminus end. You know, that you write on the structure. Then from the primary, we learned about the secondary structure where you had your alpha helix and the beta sheets due to the intermolecular force of attraction within the strands of the amino acids. No, for example, are the hydrogens. And from the secondary structure in the long range sequence of amino acid, the peptide polypeptides will assume a tertiary structure. They will fold into a tertiary structure, and from the tertiary structure, we can fold that one into the quaternary structure. Okay, and those structure of proteins actually, whether they are globular, fibrous, no, will determine its structural functions, or rather its functions, no, whether it will function in structural form, or will it function as carriers or as an enzyme or other functions that may be needed in biological system, no, as what we have discussed in the first few slides of the structure. And from this quaternary and tertiary structure, it's actually feasible, no, for this tertiary and quaternary structure to be disrupted. Okay, we call that the one denaturation. No? So they can be denatured by using different denaturing agents. For example, if we heat, no, if we heat our proteins, the affected regions or the hydrogen bonds. For example, no, you have your egg, you have your albumin, the structure or the features rather of the albumin before heating. No, it's a liquidate or soft protein. Soft protein features of the albumin. The albumin is a globular protein. So if you notice, kanang sa mga egg whites, di ba, mura siya very soft, no? It acts as a carrier. And you will notice that after heating the egg, no, it hardens siya, no? And one of the reasons is because of the hydrogen bond has been disrupted. No? The features of the original structure of the albumin has been disrupted, probably na disrupting yung tertiary, and not so much with its primary structure. It would still be albumin, but only with its quaternary, tertiary, and probably the secondary structure na disrupt. No? It's due to the hydrogen bonds being affected. If we use other agents, for example, a base like urea, hydrogen bonds also are being disrupted. What else? If you use acids and bases, it can also disrupt the hydrogen bonds, salts, salt bridges, like salt bridges. And then we can use detergents. The hydrophobic regions can be disrupted. No, the hydrophobic regions of the proteins are always embedded inside the protein structure. It's always away from the surface of the protein, because if they are hydrophobic, it's water fearing. So we use this kind of reagents. It will affect on the structures or the forces of attraction within the proteins that it will disrupt the
Excuse me,
structure.
ma'am.
Yes.
Wala na share screen, ma'am.
What about this, Nana?
Nana, ma'am.
Yeah, di ko kabisada yun sa kuan. Anyway, I was showing earlier now the structure, the hierarchy of the proteins. You start from the primary structure, and then you have the secondary structure using only the hydrogen bonds. it can be within 4 residues away, or it can be alongside the peptide structure. You can have your beta sheets, and from that you can also have your tertiary structure. You combine all the ordered structure secondary, like the alpha and beta, and the non-ordered form like the coil structures. In the long range region, the protein can fold, assume a tertiary structure, and from there it can assume a quaternary structure. Now this quaternary structure, tertiary structure, and even the secondary can actually be disrupted, by several reagents. For example, if you have heat, you can disrupt the hydrogen bond as well as the base urea. What else? Acids and bases, and it can also disrupt the hydrogen bonds. If we use the detergents, the hydrophobic regions, katong mga amino acids that are hydrophobic embedded or residing inside the tertiary structure, can be disrupted. Probably they can be exposed to the surface because of the detergent, and in the end also will affect on the structure. So ma-disrupt na siya, and it will change on the features and as well as the function of the amino acid. For example, the albumin that you can see in the egg, when you use like a heat or any reducing agent, acids, bases, or alcohols, it can be disrupted. Even the mechanical stress, to the albumin, to the protein, it will disrupt such that it couldn't function normally when they are disrupted. For example, it could still be albumin, somehow, but its function will be disrupted, cannot carry anymore its usual function when this structure is disrupted, by the reagents. It's important that our proteins are protected now when they are in biological systems. So that sums up what we learned, chapter 2, which is about proteins. And for today, we will be moving on to chapter 3, which is about the carbohydrates. So the carbohydrates are from the word carbon, and hydrates, it means the hydrates of carbon, having the molecular formula of C. They have a general formula of CH2O or C.H2O-N, so there's the number of carbon and H2O, so it's a carbon that is being hydrated. So when N is greater than 3, or CnH2OM, with this general formula, we can actually have our carbohydrates. Now, the basic of carbohydrates is what we call as monosaccharides. Okay.
Excuse me, ma'am. Muted po yata ka, ma'am.
Okay, so the carbohydrates again comes from the general word carbohydrates or carbohydrates, where it is a hydrated carbon. Generally, the number of carbons in water is usually greater than 3, you know. So this is where the normal sugars or underivatized glue, where you have all carbons or attached oxygen like in here. So most these carbohydrates, the most abundant class of biological molecules, they originate from the solar powered combinations of carbon dioxide and water in plant photosynthesis. No? And you will have your example here of the structure of the carbohydrates. Now you have 1, 2, 3, 4, 5. This is 5 carbon, and you should be able to see 1, 2, 3, 4, 5, 5 oxygen, having this formula, and you should see this 10, let's see, 3, 4, 5, 6, 7, 8, 9, 10. No? So this is an example of a carbohydrate. So there are different multiple biological functions for a carbohydrate. It can function as an energy source. We usually get low energy as humans, and even in biological systems when we are out of source sa mga carbohydrates. No? So its main function is energy source. It can also function in structural forms. It can also is one of the component of the DNA and RNA, the nucleic acids, and it also acts or present in cellular interactions and recognition events in biological systems. So many proteins from eukaryotic cells are actually glycosylated. What does this mean when we say glycosylated? It means that there are carbohydrates attached to it, sugars covalently bound to the proteins. So carbohydrates has also the common name of the sugar form. Okay, so the surface of cells also display a variety of sugar-based structures, and this is what we mean as the proteins being glycosylated or having carbohydrates attached to the proteins or sugars attached to the proteins. Next. So I have already mentioned that about 80% of human caloric intake is due to carbohydrates, and that's what I have meant earlier, that one of the functions of carbohydrate is our energy source, and the carbohydrates also comprise 90% dry matters of plants. No, any part of the plants that you can see are mostly carbohydrates. So some functional properties of carbohydrates is that they are sweet. No, it's chemically reactive, and they have a polymeric. They are polymeric in structure. Excuse me. They have polymer functionality. What do you mean by polymeric? It means that there is a repeating unit that we can see for it to become polymers, for it to become called a larger version of the carbohydrates. So carbohydrates can be classified as monosaccharides, disaccharides, oligosaccharides, or polysaccharides. No? So the monosaccharides consist only of single sugar units, while the disaccharides consist of 2 sugar units. So from the word di, no. And then oligosaccharides, we have 2 to 10 sugar units, and we have the polysaccharides more than 10 units. And there is this chain that bridge these sugar units. We call this bond to be the glycoside bond. No, if we have in the proteins, we have the peptide bond that is due to the amide bond. Then here in the carbohydrates, we also have a glycoside bond. So again, examples of the carbohydrates, the simplest one are the monosaccharides. So example are the glucose or the blood sugar with a molecular formula of C6H12O6, no? The general formula for carbohydrates again is CnH2O. You have this. So you have how many number of carbon is also the number of water that you can have. So for example, you have glucose, like C6H12O6 can also be written as C6 6 water, okay? But you can distribute on the 6 subscript here. You can actually get 12 atoms of hydrogen per 1 molecule of your glucose, and then 6 carbon, 6 also oxygen. You also have your sucrose. It's actually a disaccharide, no? It has a formula of C12H2O, O11, no? So -1. There is already hydrolysis reaction going on and sucrose being prepared. So in other words, by definition, a carbohydrate is a polyhydroxyaldehyde or polyhydroxyketone, or a substance that gives these compounds on hydrolysis. So the first structure, or the simplest structure of the carbohydrate, as I have mentioned, is the monosaccharide. And for this structure, you have in the structure, you have the aldehyde. What is that aldehyde? Aldehyde is simply C double bond O hydrogen. Okay. I think you are familiar of this already. It's C double bond O hydrogen. It cannot be like C carbon bonded to hydrogen and oxygen bonded to hydrogen. No, this is like a shorthand notation for an aldehyde. You always have to remember that carbon should always have 4 bonds. No, assumes the octet. So there should be 4 bonds to this carbon. So where is the 4 bonds coming from? The 4 bond would come from single bond here, double bond oxygen, and single bond hydrogen. Okay, so you should see, wala ipakita. You should have okay, I'll go back to this slide. So you should have an aldehyde, the monosaccharides. You'll get an aldehyde in the structure, this one, C double bond O hydrogen, and you'll get a ketone structure, C double bond O. Okay, so the simplest type of carbohydrates are, as I have mentioned, is the monosaccharide. Now, the monosaccharides are categorized by the number of carbons. Typically, they have 3 to 8 number of carbons, and either they contain an aldehyde or they contain a ketone. Okay, the most abundant monosaccharides that we have are 6 number of carbons, or the hexose. And most monosaccharides are actually aldehydes. So you have an aldehyde for a monosaccharide that contains an aldehyde like this one. We call this as an aldose. So let's have an example on the structure of the monosaccharide. So the monosaccharides, that the simplest one are the glyceraldehyde and the dihydroxyacetone. Okay, so it contains 3 carbons. It's the simplest one. As you remember, in the formula, you have a minimum of 3 carbons and of course 3 waters. You get 1, 2, 3, And then 1, 2, 3, 4, 5, 6, no, H2O. So 6 oxygen can get. So to get that one, you will have C double bond O hydrogen. This is the aldehyde part. Kaning cho, morning cho, no? Katong kaganina nga akong ipakita, that is only a short hand notation of what cho is. And this is it. And then you will have your alcohol. Remember your functional groups in organic chemistry. So there are 2 functional groups that you can see in a monosaccharide. But there are 2 types of monosaccharide. The first one is when it contains an aldehyde, and the second one is when it contains a ketone. So a ketone is when you have the structure C double bond oxygen carbon carbon. Okay, this is an R group, and you have C double bond O. This is a ketone. When you have a C double bond O and the other one is hydrogen and an alkyl group here, this is an aldehyde. Okay, so here you have the simplest monosaccharide. It's an aldose. Aldose, and when it contains an aldehyde, and you call it a ketose, and it contains a ketone. Okay, so the simplest one, its common name is glyceraldehyde. It contains 3 carbons. It's an aldotriose. Aldose because you have your C double bond O here. Tri because you have 3 carbons. And this is a keto triose. Its common name is dihydroxyacetone. If you notice, this is like an acetone here, C double bond O. The acetone would have a structure of C double bond O, CH3, CH3, dapat. But since you replace one of the hydrogens with the OH, so that's why it's called dihydroxyacetone. So this is only the common name, but there is of course an IUPAC name for that. So the IUPAC name for this is very long, no, 1, 2, 3. So it's a 3 carbon atom, and you have an aldehyde, so its parent chain should be pro, 3 carbons, and an aldehyde, it should be a propanaldehyde. Remember your organic chemistry, it should be named as propanaldehyde. So it's carbon 1, it's carbon 2, and carbon 3. So it should be 2, 3. This serve as a substituent, and we call this as a hydroxy group. And since there are 2 kinds of functional groups, we give a higher priority to an aldehyde, so this becomes a substituent. And so since we give a higher priority again to an aldehyde, so we name this the parent chain of this to the aldehyde. So that's why we name this one as we end with aldehyde. So there are 3 carbons, so it should be propanaldehyde. Okay. Propane, from the word propane, 3 carbons, propanaldehyde, and in carbon 2 and carbon 3, there is a hydroxy group, so you say that one as 2,3 dihydroxy propanaldehyde. This one you will have a ketone, so you have 1, 2, 3. This is 2 carbon 1 carbon 2, so you call this one as 2, 3 carbons, propanon, no, propane from the word propane, but there is a ketone, so we end as -one. So that's why the IUPAC for this one, second one is propanon, and it's on carbon 2. So this one on carbon 1 and carbon 3, there's an hydroxy group, so it's 1, 3 propanon. 1, 3 dihydroxy propanon. So that is the IUPAC name, but it's commonly named as dihydroxyacetone glyceraldehyde for this, which I just want you to remember how you name organic compounds. You've learned that in your organic chemistry, of course. No? So with the IUPAC name and good, you can always have an idea of what the functional groups are. But even here in the common name, it's also indicated the kind of functional groups that is contained in the structure or in the formula, no, of this carbohydrate. Okay, in particular this monosaccharide. So since you have an aldehyde in the name, you expect that there is an aldehyde in the structure, and there is an acetone on, it means there is a ketone in the structure. and the rest will be made up of the hydroxy group. So often the designations aldo and keto are omitted, and these molecules are simply referred to as triose, tetrose, and the like. So they are named or they are referred rather based on the number of carbons that are present. Okay, so again, so this is the simplest kind of carbohydrate. We call this as a monosaccharide, and the least number of carbons that a monosaccharide or any carbohydrate can have is 3 carbons. So this is the simplest one. So here we have the structure of the R-glyceraldehyde. No, it's in 3-dimensional form. Okay, and you will see that the second carbon is actually a chiral carbon. What do you mean by chiral carbon? Chiral carbon is a carbon that is bonded to 4 different groups of atoms. And because of that, okay, this chiral carbon, when you look at on the mirror image of this, the mirror image of this actually is not superimposable to this one. So we always have to be careful with chiral for compounds containing chiral carbons. Why? Because it is very important to biological system. Okay, in biological system, we all easily find the R-glyceraldehyde. No? So the 3-dimensional representation is this one. So the dark wedge means that it is directed towards you. Okay, we have a plane here, plane of the paper, plane of the phone or laptop. The vertical lines or the dark lines projected towards you, and the broken line is projected away from the plane of the laptop or plane of your phone. No, it's directed away from you. And there is what we call as Fischer projection. A Fischer projection is a 2-dimensional representation showing the configuration of the stereocenter. No? It's a simple representation where you just draw horizontal and vertical lines. So when you draw this one, no kapoy kayo mag-draw, mag-wedge pa just to show the orientation of the groups of atoms in the chiral center. So here we simply have to draw the Fischer projection. It's a simpler one. When we draw the vertical line, it means that this vertical line is directed away from you and the horizontal line is directed towards you, like this one. But the simplest, when we see something like this, where you just see some horizontal and vertical lines in the structure, it means that this is drawn in a Fischer projection. Again, this one is a 2-dimensional representation. So this is what I have mentioned earlier, that when you have your glyceraldehyde, there is actually an enantiomer or the mirror image of the glyceraldehyde. If you look this one in the mirror, okay, what you will see in the mirror is this. So if this is your mirror, for example, kaning sa center, remember your organic chemistry, what you will see in the center, okay, is that you will have your front here. What you will have is you also have your OH, baliktad OH and hydrogen, and throw and up and down you will have the same but baliktad kaning vertical. So when you have these two, try to superimpose this one. I don't know if you've used software before. No, you should, if you did in the organic chemistry, you should be able to see what the structure is, the glyceraldehyde, if they can be superimposed or not. No. Later, we will have an activity for that to show on the stereochemistry. So there's 2 kinds of the glyceraldehyde. There is the D-glyceraldehyde and there is this L-glyceraldehyde. So the D-glyceraldehyde is texturorotatory. It rotates the plane polarized light to the